Man, is this thing broken again? Come on, you piece of junk. You're not going to get me again.
Hey, Don, let me show you how to work that thing before you hurt yourself. You see, you just have to know how to talk sweet to these machines.
Yeah, well, talking sweet is not really one of my strong points.
Listen, I happen to know that one of your strong points is high energy ignition systems, right?
Yeah, that's one thing I happen to be able to handle. Why, got a problem?
Well, the only problem I have is that I don't know anything about high energy ignition. So I'd like to make you a little proposition. You fill me in on high energy ignition and its model usage, and I'll show you how to operate a vending machine.
Very funny. But I guess I can do that. First of all, let's talk about model application. The high energy ignition, or HEI system, is used on all AMC and Jeep vehicles equipped with the 4-cylinder 2.5-liter engine, beginning with the 1980 model year. Emission control technology and the more stringent fuel mileage requirements have resulted in leaner fuel mixtures in today's engines. Therefore, a hotter spark is required to fire the plug and ignite the air-fuel mixture. Conventional ignition systems can't generate a high voltage simply because their breaker points can't handle a high voltage load.
So this is why electronics are used in high energy ignition systems.
Right. The real beauty of the high energy ignition system is its simplicity. As you can see, there are only 3 principal components involved: the battery, ignition switch, and distributor. The entire primary wiring circuit consists of 2 wires. One runs from the ignition to the distributor, and the other one runs from the distributor to a tachometer pickup lead at the firewall. This system doesn't need a resistance wire between the ignition switch and coil. Also, on the HEI system, the coil has been placed inside the distributor cap, so the coil is not exposed to the elements and a high-tension coil lead isn't needed. Here are the principal components of the distributor. The distributor cap assembly consists of the coil cover, the ignition coil, and the distributor cap. The lower housing assembly contains the rotor, the electronic module, the magnetic pickup assembly, and the connector. The coil cover, which protects the coil from moisture and dirt, is secured to the cap by 2 hex head screws. The coil is actually 2 individual windings covered by epoxy insulation. This assembly is contained in an iron frame. As you can see in this cutaway view, the primary winding is located next to the iron core. This design differs from a conventional coil design, in which the secondary winding is positioned next to the core. And here's the distributor cap.
Don, this cap is quite a bit larger than a conventional cap, isn't it?
Yeah, it has to be, for 2 reasons. First, it has to house the coil assembly. Also, this large size prevents high-voltage arc-over. You see, the HEI cap is designed so that there is wide spacing between the cap inserts. Without this spacing, the high-voltage spark could arc between the inserts, causing all kinds of problems.
That makes sense.
The rotor is mounted by 2 screws to the centrifugal advance mechanism on top of the distributor drive shaft. The spring and button in the cap conduct voltage from the coil output terminal to the rotor. The rotor then supplies the voltage to the spark plugs via the cap inserts.
I see that the rotor can only go on one way due to the locating tab.
Yep, this one's foolproof. The distributor shaft assembly consists of the centrifugal advance mechanism, timer core and shaft, washer, spring, spring retainer, and gear. As we'll see shortly, the timer core rotates inside of the magnetic pickup assembly when the engine is running. Here are the components of the magnetic pickup assembly. As you can see, a donut-shaped permanent magnet and pickup coil are sandwiched between a pole piece and bottom plate. The bottom plate fits over a bushing in the distributor housing. A tab connects the plate to the vacuum advance unit. The electronic module contains a micro-miniature electrical circuit with components so small that they can't even be seen with a magnifying glass.
So how do all these components work?
I'll get around to all that in just a minute. But first, I want to point out how the electrical components of the lower distributor assembly are joined to the ignition coil terminals. As you can see here, the connector body latches slip over 2 notches in the cap. The battery terminal is where the wire from the ignition switch connects to the distributor. The tachometer pickup is located on the firewall of our vehicles. The other end of the lead wire connects to the terminal shown here. And before I explain exactly how the system works, let me just refresh your memory with a couple basic principles. This first principle is illustrated here. When electric current flows through a wire, a magnetic field is created around the wire. Additionally, if the wire is wrapped in a coil, a greater magnetic field is created. If an iron core is inserted inside the coil, as shown here, the magnetic field becomes even stronger. On the left here, a second coil has been placed over the first coil, inside the magnetic field. On the right, the current flow to the first coil has been interrupted, causing the magnetic field to collapse. This results in a new voltage being created in the second coil. This new voltage is called induced voltage. Let's see how this principle is applied in the HEI system. Remember that the timer core is continually rotating inside the magnetic pickup assembly. Here's what happens when the timer core teeth line up with the teeth on the pole piece. A strong magnetic field from the permanent magnet is established through the center of the pickup coil. This produces an induced voltage in the pickup coil, which signals the electronic module to open the ignition coil's primary circuit. When the primary coil circuit is opened, the primary current decreases. This decrease, in turn, collapses the magnetic field and induces a high voltage in the secondary winding. This high voltage is then conducted to the spark plug to ignite the air-fuel mixture. As the timer core continues to rotate, the teeth no longer line up with the teeth on the pole piece. As a result, the module turns the primary circuit back on. This continual on-off activity is what induces the secondary voltage in the secondary winding and fires the spark plugs.
Actually, this system seems pretty easy to understand.
It is.
If memory serves me right, the voltage from the secondary coil should be much higher than the primary circuit, right?
Yeah, it is. The HEI secondary winding has about 100 times as many turns as the primary winding. The wire in the secondary winding is also only about 1/2 the diameter of the primary's wire. This graph illustrates how engine speed and spark plug condition dictate spark plug voltage requirements. The green line at the top indicates the maximum levels of voltage available at various speeds. The dotted red line represents the voltage needed to fire used plugs at the various speeds. And the solid red line represents the voltage requirements of new plugs. You can plainly see that new plugs require much less voltage than used plugs. Here are some other factors that influence spark plug voltage requirements: the engine's compression ratio, deposits on the plugs, the shape of the electrodes, and plug gap.
What happens if, for any reason, the voltage requirement happens to exceed available voltage?
The plug won't fire, just as it won't on a conventional system. There's one more area to look at: the centrifugal and vacuum advance units. Essentially, these mechanisms perform the same functions as their counterparts on a conventional system. That is, they advance the spark as is needed under certain conditions to obtain maximum fuel and power efficiency. On the left here, this engine is idling, and the spark is timed to occur at 8 degrees before top dead center. The mixture will have burned completely before the piston reaches 10 degrees past top dead center. This is a necessity in order to achieve maximum power. At higher engine speeds, though, there's a shorter interval of time available for the fuel-air mixture to ignite, burn, and give up its power to the piston. So now, at 2,000 RPMs, the spark has to occur earlier in order for the mixture to be completely burned when the piston reaches 10 degrees past top dead center. Here's how this advance is achieved. On the right, the engine and distributor shaft speed have increased, causing the weights to fly out against their spring tension. This causes the timer core to turn on the shaft in the direction of rotation. The teeth align sooner, and the spark occurs earlier. The HEI system, like conventional systems, also requires a spark advance feature under part throttle. This is facilitated by the vacuum advance mechanism. On the right here, the vacuum advance has been activated. When the diaphragm is compressed, the advance linkage rotates the magnetic pickup assembly against the direction of timer core rotation. The teeth line up sooner, and the spark is advanced. Really, Sue, there are only two potential problem conditions that you might have to diagnose and correct. The engine won't start, or it starts and runs rough. If you have a situation where the engine won't start, the first thing to do is make sure the problem isn't in the fuel system. Have someone crank the engine over while you observe the fuel flow. Be sure to use a container to catch the fuel. Next, perform a spark test. First, check for battery voltage at the distributor. Connect one lead of a voltmeter to the battery terminal lead on the distributor. Connect the other lead to a good ground. Then turn the ignition switch to the on position. If your voltage reading is 0, you've got an open circuit between the distributor and the battery. If your reading is equal to battery voltage, install an extension lead in the plug boot. Use insulated pliers to hold the extension lead about a 1/4 inch from a dry area of the block while someone cranks the engine over. If sparking occurs during this check, your problem is not in the ignition distributor. If you don't get any spark, you'll have to test the individual components. So, at this point, remove the cap and inspect the cap and rotor. Replace them if you find any damage. Here's how you can test the coil. Connect an ohm meter as shown here and take a reading. If this reading is more than 5 ohms, replace the coil. If it's less than 5 ohms, proceed to step 2. Connect the ohm meter, as shown here, and take a reading. If this reading is not infinite, the coil should be replaced. Finally, connect the ohm meter as shown here and take another reading. If this reading is not infinite, the coil should be replaced. Now, check the pickup coil by connecting your ohm meter and vacuum pump, as shown here. If you get a reading other than infinite with no vacuum applied, replace the pickup coil. Next, observe the ohm meter as you apply vacuum to the advance mechanism. If your reading is not infinite throughout the entire vacuum range, replace the pickup coil. To perform the third step of the pickup coil test, connect the ohm meter and vacuum pump, as shown here. With no vacuum applied, your reading should be between 500 and 1500 ohms. If this reading is less than 500 ohms or more than 1500 ohms, replace the pickup coil. Finally, observe the ohm meter throughout the entire vacuum range. This reading should always be between 500 and 1500 ohms.
I can see that a voltmeter and an ohm meter are necessities if you're going to work on HEI.
Definitely. Now, if you do have to replace a pickup coil, follow this procedure. You'll have to remove the timer assembly, so begin by preloading and locking the spring to its retainer. Next, remove the drive pin from the shaft. With the pin out, you can remove the gear. Remove the C-washer. With the washer removed, you can remove the pickup coil assembly and install a new one. Then, reassemble the unit. Here's an important note. When you reassemble the distributor gear and shaft assembly, be sure that the drill mark on the gear is in the same half of the rotor's arc as the rotor tip. Here's an important warning, Sue. Never loosen the screws that join the pole piece to the pickup coil. These units are assembled to very close tolerances, which must not be altered. Poor connections at the module terminals can cause big problems in an HEI system. Experience has taught me to clean the terminals with a wire brush or emery cloth whenever I service an HEI system. This removes any oxide film, which can cause resistance in the system. Inspect the terminal-to-wire connections. If they're loose, take the time to resolder them. To reduce oxidation in the future, apply a thin coating of petroleum jelly to all the module terminals. Inspect the module base to make sure that there's a small amount of silicone heat transfer grease present on the base. If there isn't, be sure to apply some. Now, let me give you some quick troubleshooting tips to use if you get an engine that starts but runs rough. Always look and listen for sparks jumping to ground from a defective plug or plug lead. The timing could be off, so at this point, it's a good idea to connect a vacuum pump to the vacuum advance unit to make sure the advance unit is working properly. If the vacuum unit is defective, replace it.
How about the mechanical advance mechanism?
Check that too. It only takes a minute to give the weights a little workout. Then make sure that the initial timing is set to the correct spec. Spark plugs are infamous for being trouble sources, so it's worthwhile to check the plugs.
Don, what if you've done all these things and you still haven't found what's causing the engine to run rough?
Well, if that's the case, you'll have to test the individual HEI components. To do this, follow the steps we covered when we talked about what to do if the engine won't start. And that, Sue, is the high energy ignition system. Any questions that I can answer for you?
No, I have to say you've about covered it all.
Be sure to hang on to this reference book that accompanies this film. It contains all of the troubleshooting procedures we discussed today.